What specific problem does your study aim to address regarding the learning rate, LR, in neural network training? And what is the significance of identifying the subregime 2A in this context?
The study aims to address the lack of a unified understanding of how different learning rates, LRs, affect the training outcomes of neural networks, particularly the optimal range of LRs that lead to better generalization. Specifically, it investigates the characteristics of models trained with varying LRs and identifies the significance of subregime 2A, which is a narrow range of moderately high LRs that avoids both convergence and divergence. Training within this subregime consistently yields optimal results, as it locates a convex basin in the loss landscape containing well-generalizing minima. This finding is crucial because it suggests that starting training with LRs from subregime 2A allows for effective fine-tuning or weight averaging, leading to better model performance compared to using too small or too large LRs. Ultimately, identifying subregime 2A provides practical guidance for selecting initial LRs that enhance the training process and improve the generalization capabilities of neural networks.
Can you explain how your proposed method for analyzing the impact of different initial LRs on neural network training operates? Please illustrate it step by step, detailing how you categorize the training regimes and what each regime signifies.
Our proposed method for analyzing the impact of different initial learning rates, LRs, on neural network training operates through a structured empirical analysis that categorizes training into three distinct regimes based on the behavior of the optimization process. First, we define the regimes. 1. Regime 1, convergence. In this regime, small LRs lead to stable convergence towards a minimum, but often to suboptimal solutions with poor generalization. The training loss decreases to low values, indicating successful convergence. 2. Regime 2, chaotic equilibrium. This regime is further divided into two subregimes. Subregime 2A, characterized by moderately high LRs that do not lead to convergence or divergence, allowing the model to locate optimal regions for further fine-tuning or weight averaging. Models trained in this subregime exhibit high-quality solutions and good generalization. Subregime 2B. Higher LRs in this subregime begin to degrade the quality of solutions, leading to diverse minima that are less effective for fine-tuning. 3. Regime 3, divergence. In this regime, the model fails to converge, exhibiting random behavior akin to random guessing. Training in this regime is impractical for weight averaging, but may still provide some benefits for fine-tuning with small LRs. By categorizing the training into these regimes, we can systematically evaluate the generalization performance and feature learning characteristics of models trained with different initial LRs, ultimately identifying the optimal range for effective training.
Could you provide a detailed example from your analysis that shows how the effective learning rate, ELR, varies across different learning rate values and how this impacts generalization?
In our analysis, we observed that the effective learning rate, ELR, varies significantly across different learning rate, LR, values, particularly when training in the second regime, which we subdivided into subregime 2A and subregime 2B. For instance, when pre-training in subregime 2A, we found that models trained with lower PLRs within this regime consistently achieved better generalization compared to those trained with higher PLRs in subregime 2B. Specifically, pre-training in subregime 2A allows the model to locate a convex basin in the loss landscape, which contains well-generalizing minima that can be effectively fine-tuned with smaller LRs. In contrast, models trained with higher PLRs in subregime 2B not only failed to find these optimal basins, but also exhibited a diverse set of minima, leading to poorer generalization. This demonstrates that the ELR, influenced by the choice of initial LR, plays a crucial role in determining the quality of the solutions found during training, as it directly affects the model's ability to learn relevant features and achieve optimal performance.
What empirical results did you obtain regarding the generalization performance of models trained in subregime 2A compared to those trained in other regimes? And what implications do these results have for practical applications of learning rate scheduling?
In our empirical analysis, we found that models trained in subregime 2A consistently achieved superior generalization performance compared to those trained in other regimes. Specifically, pre-training in subregime 2A resulted in models that could be fine-tuned with any small learning rate, FLR, while still reaching high-quality minima, which was not the case for models trained in the first regime or higher subregime 2B. The results indicated that starting training with learning rates from subregime 2A allows for the localization of a convex basin containing optimal solutions, facilitating effective fine-tuning or weight averaging. This suggests that in practical applications, it is crucial to select an initial learning rate just above the convergence threshold and to design a learning rate schedule that allows for gradual adjustments, ensuring that the model can explore and settle into regions of the loss landscape that yield better generalization. Overall, our findings emphasize the importance of both the initial learning rate and the subsequent learning rate schedule in achieving optimal model performance.
How did you validate the effectiveness of your proposed method? Please specify the datasets used, the experimental design, and the performance metrics applied to ensure a rigorous evaluation of your findings.
To validate the effectiveness of our proposed method, we conducted experiments using the CIFAR-10 dataset, along with additional evaluations on CIFAR-100 and Tiny ImageNet datasets, as detailed in the appendix. Our experimental design involved training a scale-invariant RESNET18 model with different initial learning rates, PLRs, across 3 defined training regimes, specifically focusing on the second regime, which we subdivided into subregime 2A and subregime 2B. We assessed the generalization performance of the models by evaluating their test accuracy after pre-training and subsequent fine-tuning or stochastic weight averaging, SWA. Performance metrics included test accuracy and the analysis of angular distances and linear connectivity between solutions, which provided insights into the quality and stability of the minima reached. This rigorous evaluation framework allowed us to confirm that pre-training in subregime 2A consistently yielded optimal results, demonstrating the importance of the initial learning rate in achieving high-quality solutions.
What limitations did you encounter when implementing your method, particularly regarding the applicability of your findings to real-world problems or scenarios?
One limitation encountered when implementing our method is the challenge of applying the findings from a controlled experimental setup to more complex real-world scenarios. In practical settings, the behavior of neural networks can be influenced by factors such as data augmentation, which complicates the clear distinction between training regimes and may hinder convergence with small learning rates. Additionally, while our results indicate that starting with higher learning rates can lead to better solutions, the exact learning rate schedule must be carefully designed to avoid rapid decreases that could prevent the model from localizing optimal basins. Furthermore, the presence of spurious features in real-world data can lead to different feature learning behaviors, which may not align with the sparse feature selection observed in our experiments. These complexities suggest that while our findings are promising, they require further exploration to fully understand their implications in diverse practical applications.